Section 1 Introduction. In our introduction, we dive into the world of large language models, LLMs, and their impressive accomplishments across numerous natural language processing tasks. These LLMs have shown promising steps towards achieving aspects of broad-spectrum artificial intelligence, akin to the complexity of human intelligence. In light of these observations, the possibility of enhancing LLMs with external tools has emerged. This approach can significantly improve their problem-solving skills and efficiency, much like the evolution of human intelligence that saw us start to use tools. But, the effectiveness of this tool-using approach heavily depends on having suitable tools at hand. Drawing parallels from the evolution of humans, a pivotal moment was when we learned to create our own tools to tackle emerging challenges. This historical precedent sparks an idea. What if we could apply this tool-making concept to LLMs? Inspired by this thought, we propose an innovative framework called LLMs As Tool Makers, LATM. This framework empowers LLMs to design their own reusable tools for handling new tasks. We've structured our approach into two main stages. The first is toolmaking. Here, an LLM we call the tool maker constructs tools, expressed as Python functions, explicitly for a given task. The second stage is tool using. Another LLM, the tool user, which could be the same entity as the tool maker, uses these tools to manage new tasks. This two-step design enables LATM to assign roles in each stage to the most appropriate LLM. For instance, the tool-making process, which demands a high level of capability, might be handled by a highly competent but resource-intensive model like GPT-4. On the flip side, the tool-using process, which is simpler, could be assigned to a more lightweight and economical model like GPT 3.5 Turbo. This approach not only bolsters the problem-solving abilities of LLMs but also significantly cuts down the average computational cost for addressing a series of tasks. Since the tool-making process only needs to be executed once for each functionality, the resulting tools can be reused across different tasks. This method lays the foundation for a scalable and cost-efficient solution for managing complex tasks. Let's consider a situation where a user asks an LLM to arrange a meeting at a time that suits everyone, perhaps via email conversation. Lightweight models, like GPT 3.5 Turbo, often struggle with such tasks that require complex arithmetic reasoning. However, more powerful models like GPT-4 can find the correct solutions, albeit at a higher computational cost. LATM navigates these obstacles by leveraging a powerful, albeit expensive, model as the toolmaker, and then passes the created tool to a more cost-effective model as the tool user for subsequent use. After the tool has been created, the lightweight tool user can utilize it to efficiently solve the task with high performance. This principle can be applied to recurring tasks in various workflows, like parsing and analyzing web documents into specific data formats, formulating routing plans that fulfill multiple custom requirements, or even solving popular games like the 24 game or Sudoku. Moreover, we introduce another lightweight LLM, the dispatcher. The dispatcher assesses whether an incoming problem can be solved using existing tools or if a new tool needs to be created. This additional layer injects more dynamism into our framework, allowing for real-time, on-the-fly tool making and usage. Our experiments confirm the effectiveness of this approach on a variety of complex reasoning tasks, including several challenging big bench tasks. The results demonstrate that LATM can match the performance of more resource-intensive models while remaining more cost-effective. This pioneering approach to LLMs, which mirrors humans' evolutionary progression in creating and using tools, opens up thrilling possibilities for a growing community with LLM-generated tools. Section Summary. The paper proposes a closed-loop framework called LLMs As Tool Makers, LATM, that enables large language models, LLMs, to generate their own reusable tools to tackle new tasks. The approach comprises two stages, tool making and tool using, which allows LATM to allocate jobs to the most suitable LLM. This approach enhances the problem-solving capabilities of LLMs, significantly reduces the average computational cost of addressing a series of tasks, and opens up exciting possibilities for a growing community with LLM-generated tools. Section 2 Related Work. Point 2. Related work. Thought chain, COT. Recently, there have been impressive strides in improving the problem-solving skills of large language models, LLMs, for intricate tasks. For example, an approach known as COT prompting has been introduced to fortify the reasoning abilities of LLMs, showcasing better performance on diverse reasoning and natural language processing tasks. While thought chain, COT, is usually expressed in common languages, it can also be effectively communicated using programming languages. There's also been recent interest in employing LLMs to generate structured summaries of documents, creating a balance between the quality and the cost of the process by assembling extractions from several synthesized functions. Our method aligns with this approach in the way we handle the trade-offs between quality and cost, but we aim to cover a wider array of applications. Expanding language models with tools. There has been burgeoning interest in exploring how external tools can enhance the abilities of LLMs in handling complex tasks. The idea of enriching reasoning paths with task-specific actions within LLMs has been proposed, allowing the models to reason and perform actions in harmony. Several studies have shown that supplementing LLMs with tools, calculators, search engines, translation systems, calendars, or even API calls on other models can assist in resolving tasks that are usually tough for LLMs to solve alone. Our approach is akin to others such as Chameleon that incorporate Python executors in their systems. Yet, these methods typically focus on leveraging Python executors to precisely resolve subtasks that involve arithmetic reasoning. In contrast, we employ Python executors to construct reusable tools to address different task instances. Moreover, by distinguishing between the toolmaker and the tool user, we are able to leverage a more lightweight model for most inferences, thereby improving the efficiency and cost-effectiveness of our approach, which we refer to as LATM. Section Summary. Recent research has shown that chain-of-thought (COT) prompting can improve the reasoning capabilities of large language models (LLMs) for various natural language processing tasks. Additionally, studies have explored the potential of using external tools, such as calculators or search engines, to supplement EM's capabilities for complex tasks. The proposed method, Lightweight Augmented Task Models (LATM), uses Python executors to create reusable tools for addressing various task instances, enhancing efficiency and cost-effectiveness. Section. Adaptive Generation in Language Models. We've been actively exploring adaptive generation in language models. Recent studies have suggested ways to enhance the efficiency of text generation in large language models, LLMs, by intelligently controlling the decoding process. The concept of speculative decoding is a standout example. It works under the principle that the generation of text tokens, which is a time-consuming process, can be speeded up using a simpler, faster model. It approximates the performance of larger, more resource-demanding models by using these models to quickly rate the generated tokens. This approach is about using a faster, smaller model to perform tasks originally assigned to a larger, more expensive model, all the while maintaining a high degree of accuracy. This idea is akin to adaptive computing. But we've gone a step further. Instead of just modifying the decoding process, we are pioneering an approach where we transfer newly generated tools from one model to another. This not only enhances the effectiveness of an LLM in completing tasks but also increases its efficiency. Another exciting area is the use of language model cascades. Recent studies have shown that LLMs can be set up to interact repeatedly, and combining multiple LLMs can amplify their capabilities. Furthermore, research has shown that identifying the best combinations of LLMs can lead to reduced costs and improved accuracy. We've taken inspiration from these findings. But rather than just linking LLMs, we classify tasks that could be better accomplished using new tools developed by a larger model. Then, we assign each individual task within that category to a smaller model. Section Summary. Recent research has proposed adaptive methods to improve text generation efficiency in language models, LLMs, by using faster yet less powerful models to generate text tokens and larger models to score them. Another approach is to transfer newly generated tools between models to boost both performance and efficiency in solving tasks, rather than cascading LLMs. Identifying optimal LLM combinations can help reduce costs while improving accuracy, and assigning individual inferences within a task category to a smaller model can better address the task. Section 3. In Section 3.1, titled, Making New Tools and Reuse Them, we delve into the concept of the Large Language Model Toolmaker, LATM, approach, which is divided into two main stages, the creation of tools and their subsequent usage. These stages apply different versions of large language models, LLMs, optimizing the balance between performance and cost. Let's examine the tool-making stage more closely. This step harnesses the power of a highly capable, albeit pricier, model such as GPT-4, which serves as the toolmaker. The primary function of the toolmaker is to generate versatile, reusable tools, in the form of Python functions, based on a handful of task demonstrations. We further divide this stage into three phases. 1. Tool proposing. Here, the toolmaker strives to formulate a Python function that can resolve the task demonstrations presented. This approach is guided by the programming by example principle, which involves providing specific demonstrations and tasking the model with crafting programs that replicate the demonstrated behaviors. We typically use 3 demonstrations at this stage. If the proposed tool fails to execute or encounters errors, the toolmaker logs the error messages and attempts again. 2. Tool verification. In this phase, the toolmaker generates unit tests using validation samples, which are then run on the proposed tool. We typically utilize 3 validation samples for this purpose. If the tool fails any of the tests, the toolmaker logs the error and attempts to fix the issues within the unit tests. Notably, this procedure only adjusts the function calls in the unit test section, leaving the function itself unaltered. This phase serves a dual purpose. It demonstrates how to translate natural language queries into function calls, and it verifies the tool's reliability, enabling full automation of the process. 3. Tool wrapping. If the execution or verification repeatedly fails beyond a set limit, we consider the tool-making stage to be unsuccessful. However, if it's successful, the toolmaker proceeds to prepare the wrapped tool for the tool user. This final step involves packaging the function code and illustrating how to convert a task into a function call. These illustrations are taken from the tool verification phase, where questions are converted into unit tests. The resulting product is now prepared for use by the tool user. Please see the appendix for examples of these. Wrapped tools. Section summary. In the LATM paradigm, the process is divided into tool making and tool using stages, each utilizing different types of large language models, LLMs. The tool-making stage involves using a powerful yet expensive model, such as GPT-4, to create a generic and reusable tool from a few task demonstrations. This stage includes tool proposing, tool verification, and tool wrapping substages, which generate a Python function, verify its reliability, and prepare it for use by the tool user. Section: Tool using. In the second stage of our approach, we use a cost-effective model like GPT 3.5 Turbo, which plays the role of the tool user. The primary role of this tool user is to take advantage of the verified tool to handle various versions of the task at hand. To do this, we feed the model a wrapped tool, which contains both the solution function for the task and demonstrations of how to translate a task question into a function call. Using these demonstrations, the tool user can then generate the necessary function call, following an in-context learning approach. The tool user then executes these function calls to solve the task. If necessary, we can apply some post-processing to modify the output so that it aligns with the specific format requirements of the task, such as formatting answers for multiple choice questions. It's important to note that we only need to go through the tool-making phase, which includes proposing, verifying, and wrapping the tool once for each type of task. We can then reuse the developed tools for all variations of that task. This makes our approach, LATM, considerably more efficient and cost-effective compared to using a more powerful model on its own. Moreover, our Python function tools serve as a more universal form of the chain of thought concept, thereby enhancing the overall usefulness and versatility of our language models. This is because they can be employed to solve questions that require algorithmic reasoning abilities. To give a more concrete example of our method, we've included a figure that shows how the toolmaker handles a logical deduction task from Big Bench. In this task, the model needs to infer the order of 5 objects and answer a question about them. The conditions for this task involve both the relative positions of some object pairs and the absolute positions of some other objects. To solve this task, our toolmaker, for instance, GPT-4, generates a general program that solves it by extracting constraints from the question and then searching through all possible permutations to find the result. Our tool user, for instance, GPT 3.5 Turbo, can then utilize this program to solve the task by making a function call that simply extracts relevant information from the natural language instances of the task. For additional examples of newly created tools for solving different tasks, you can refer to the appendix. Section summary. The second stage of the methodology involves a lightweight and cost-effective model, such as GPT 3.5 Turbo, to serve as the tool user. The tool user utilizes the verified tool to solve various instances of the task by generating the required function call in an in-context learning fashion. The resulting tools can then be reused for all instances of that task, making the methodology significantly more efficient and cost-effective than using a powerful model alone. Section 3. In real-world applications, tasks typically come in one after another. To handle this, we've introduced a third component to our system, which we call the dispatcher. This dispatcher decides whether to involve the tool user or the toolmaker for each incoming task. While our dispatcher may remind you of the tool selection features found in other systems, ours is unique. It has the ability to recognize new tasks that current tools can't tackle and engage the toolmaker to create new tools for these tasks. Here's how it works. The dispatcher keeps track of the existing tools that the toolmaker has produced. Whenever a new task comes in, the dispatcher first checks if there's a suitable tool available. If there is, the dispatcher sends the task and the appropriate tool to the tool user to get the task done. If no suitable tool is found, the dispatcher treats the task as a new one. It then either uses a powerful model to solve the task or asks a human labeler for help. The tasks that are identified as new are stored until there are enough of them for the tool maker to create a new tool. You can see a visual representation of the dispatcher's workflow in the figure. As the dispatcher's role is fairly straightforward, it can be a simple model with appropriate prompts. You can find these in the appendix. This means it adds only a minor extra cost to the overall system. Section Summary. The paper introduces a third LLM, the dispatcher, to handle streaming data in real-world scenarios. The dispatcher determines whether to engage the tool user or tool maker for each incoming task and can identify new tasks that cannot be addressed by existing tools. If no appropriate tool is found, the dispatcher identifies the instance as a new task and solves the instance with a powerful model or even invokes a human labeler. Section Datasets. We've tested our methodology on a variety of 6 datasets from different fields, namely logical deduction, tracking shuffled objects, Dyke language, word sorting, Chinese remainder theorem, and scheduling meeting. The first 5 of these datasets were obtained from a collection known as Big Bench. For the logical deduction and tracking shuffled objects tasks, we specifically selected the versions involving 5 objects, and will refer to these as logical deduction, 5, and tracking shuffled objects, 5, in this discussion. We also crafted a task called scheduling meeting to showcase how our method, LATM, can be effectively applied in real-world situations. You'll find more information about how these datasets were generated in the appendix. Each dataset was split into training, validation, and testing sets, with the first 2 containing 3 instances each, and the last one containing 240 instances. When it comes to the model settings, we introduced a bit of randomness into the tool-making phase by setting the temperature parameter to 0.3. This allows us to retry the process if necessary. In this phase, we utilized GPT-4 and GPT-3.5 turbo models through the chat completion API, always adding the response to the chat history to foster an interactive environment. In contrast, during the tool-using phase, we made a single call to the LLM API and also conducted ablation studies on models based on GPT-3 using the standard completion API. The temperature was always kept at 0.0 when using the tools. We established a limit of 3 attempts for proposing and verifying tools. Section Summary. The authors evaluate their approach on 6 datasets from diverse domains, including logical deduction, tracking shuffled objects, Dyke language, word sorting, Chinese remainder theorem, and scheduling meeting. They divide each dataset into training, validation, and test sets, containing 3, and 240 instances, respectively. During the tool-making stage, they set the temperature to 0.3 to introduce randomness to the generation process, allowing for retries if necessary, and conduct experiments using GPT-4 and GPT-3.5 turbo models with the chat completion API. In the tool-using stage, the LLM API call is made only once, and they perform ablation studies on GPT-3 type models with the standard completion API. Section 4. In the phase of tool creation, we employ a highly competent but relatively slow model to create generic Python functions that are task-specific. This process is carried out just once for every task, thereby spreading the associated costs across all instances of that particular task. In our experiments, we've chosen GPT-4 to exemplify the role of the tool creator, and we delve into the tool creation potential of other models in a later section. To direct the language model in the generation of generic Python programs, we provide it with a few guiding examples, as shown in a figure in the original paper. We've noticed that GPT-4, when used in the capacity of a tool creator, often comes up with suitable algorithms to tackle tasks. For example, in one of our experiments, shown in a table in the original text, the tool creator developed the code to resolve a logical deduction task. It did so by searching through all possible arrangements and selecting the appropriate one that meets the specified constraints. In our experiments, the tool verification stage primarily serves to provide examples illustrating how to translate natural language queries into function calls. We noted only 2 instances out of 60 trials where the tool creator could correct its errors with the help of error messages. We'll delve deeper into the tool creator's role in a later section. Section Summary. The tool-making stage involves using a slower model to generate Python functions tailored to a specific task, which is performed only once for each task. GPT-4 is used as a representative toolmaker, and it frequently devises suitable algorithms for solving tasks. The tool verification stage is mainly used to provide examples that demonstrate how to convert natural language questions into function calls. Section 4. In Section 4.3, we discuss how the Language Agnostic Tool Maker, LATM, bolsters the effectiveness of lightweight language learning models, LLMs. To illustrate this, we present a table where we've compared the effectiveness of the chain of thought, COT, prompting method with LATM. In our study, we've used GPT-4 as the toolmaker, responsible for creating tools for 6 different tasks. We then measured the performance of both GPT 3.5 Turbo and GPT-4 when they used these tools. The findings were quite interesting. It appears that, with the aid of the tools generated, a lighter model such as GPT 3.5 Turbo can perform just as well as GPT-4. This outperformed the results achieved through the COT prompting method by a significant margin. Moreover, it's important to note that the average cost of using GPT 3.5 Turbo, alongside these tools, is substantially less than the cost of using GPT-4. This underscores the efficiency of LATM, as it not only enhances the performance of lightweight models, but also curtails the costs associated with using more expensive models. Even more intriguing was our observation during the Dike language task. In this particular task, GPT 3.5 Turbo, when acting as the tool user, managed to outdo GPT-4, which was also in the role of tool user. On examining the cases where our models failed, we noticed that GPT-4 occasionally tackled parts of the problem unnecessarily while converting the question into a function call. This led to errors in the function's output. Section summary. The LATM method improves the performance of lightweight LLMs, as demonstrated by comparing it to chain of thought prompting. The results show that with the help of the tool, a lightweight model like GPT 3.5 Turbo can achieve performance on par with GPT-4, significantly outperforming COT prompting, and at a lower cost. Additionally, GPT 3.5 Turbo even surpasses GPT-4 in the Dike language task as the tool user due to GPT-4 occasionally solving part of the problem unnecessarily. Section 4. We're discussing the application of our LATM model to a dynamic environment where various tasks appear sporadically. In this context, we need an additional model, known as a dispatcher, to determine the relevant task for a given instance. For this role, we utilize GPT 3.5 Turbo and evaluate its proficiency in 2 main areas. 1. Recognizing the appropriate tools to solve a new instance. 2. Triggering the development of tools for tasks that have not been encountered before. Let's start with the dispatcher's capacity to identify the correct tools. To test this, we generate a random assortment of the 6 tasks discussed earlier, creating a test set with 100 samples. For every instance in the test set, we employ the dispatcher to locate the suitable tool. We give it a prompt that includes examples of tasks for which tools already exist, as demonstrated in the appendix. A successful identification of the tool is considered a correct result. We found the dispatcher to be highly accurate, with a success rate of 94% plus or minus 2%, based on 5 different randomly generated test sets. Section summary. The paper proposes extending LATM to a streaming setting with a mixture of tasks, which requires a dispatcher model to determine the task to which an instance belongs. The study evaluates the dispatcher's ability to identify existing tools and request tool making for instances from an unseen task, achieving a 94% accuracy rate in identifying the correct tool. Section. Requesting tool making. We're now going to evaluate how well the dispatcher performs when it comes to requesting the creation of tools for unseen tasks. We start by randomly choosing 4 tasks that already have associated tools. Then, we select another 4 tasks to test the system. 2 of these are completely new, while the other 2 are from the initial set of tasks. We generate a test set composed of 100 instances. For each one, the dispatcher decides whether a new tool needs to be created, or if an existing tool can solve the problem. The dispatcher proved quite successful, making correct decisions 95% of the time, plus or minus 4%. These findings demonstrate that the dispatcher can efficiently recognize existing tools and request the creation of new ones for unseen tasks, without a significant decline in performance. This implies that our tool-making approach, which we call LATM, can be readily expanded to a continuous task setting with a variety of different tasks. Next, let's look at the computational demands of the language model used in the tool creation phase. Generally, we discovered that a more powerful, although more costly, model performs better. This is because the tool creation stage only happens once per task, and high accuracy is crucial to successfully transfer the tools to a smaller model. For instance, on complex tasks like logical deduction and tracking shuffled objects, the GPT 3.5 Turbo model consistently failed in all 5 trials. This was primarily due to the fact that the tool created was not versatile enough, only working on the instances it was trained on. On the other hand, we found that for simpler tasks, a more lightweight language model can suffice as a tool creator. For example, GPT 3.5 Turbo was able to easily generate a program that could solve a basic task like word sorting. Another issue that could limit the effectiveness of the tool creator is the constraint on context length. To increase the reliability of the tool creation stage, we use the complete history of each tool-making step, which leads to a longer context. In such cases, a model like GPT-4, which can handle a context length of 8,192, is a better choice. Section Summary. The dispatcher can effectively identify existing tools and request tool making for unseen tasks with 95% accuracy. A more powerful and expensive language model is required for the tool-making stage, especially for hard tasks like logical deduction and tracking shuffled objects. However, for easy tasks like word sorting, a lightweight language model like GPT 3.5 Turbo can effortlessly generate a program that solves the task. Section. Capacity required for the tool using language model. We're now going to delve into the capacity requirements of our tool using language model. In a nutshell, we found that the GPT 3.5 Turbo model struck an excellent balance between performance and cost compared to all the models we evaluated. Let's discuss a bit more about the older models from the GPT-3 series, namely Ada, Babbage, Curie, and DaVinci. Surprisingly, these models often outperformed their newer versions that had undergone an instruction tuning process. This suggests that this tuning might have unintentionally undermined their ability to learn in context, a critical skill for the tool using phase. Next, we evaluated another method, using the chain of thought, COT, approach. Just like we did with the language as a tool model, LATM, we attempted to enhance task performance by transferring the COT from a larger model to a smaller one. To put this into action, we used GPT-4 for creating the COT by encouraging it to think step by step. The COT produced was then employed by the smaller tool using model, GPT 3.5 Turbo. After testing this approach on 2 tasks, we found that using the COT from a larger model either resulted in similar or worse outcomes than using a human-written COT. This was significantly less effective than when we used the LATM approach. In short, COT as a tool did not yield the improvement we were hoping for. Section Summary. The study investigates the capacity requirements for the tool using language model and found that GPT 3.5 Turbo offers the best balance between performance and cost. The study also explores the possibility of reusing chain of thought, COT, from a larger model to a smaller model but found that it has a similar or even worse performance than human-written COT, which is much worse than LATM.